Hi, today let's talk about session 8.3, infinite series. Sometimes when you add up an infinite set of numbers, you get a finite answer. For this to happen, most of the numbers in that set had better be pretty darn close to zero. Thus, if the terms in a sum do not tend to zero, the sum will diverge. Big skills, you should be able to compute the sum of an infinite geometric series and then use some basic tests to determine whether a series converges. Okay, so last time we talked about sequence. So today we're going to talk about series. So sequence, we know sequence is a list of numbers. Okay, so we have the sequence A sub n. Okay, and for the sequence, we can talk about the limits of the sequence. Okay, if we get a number, then we say the sequence converges. So if we get the limit does not exist, we will have the sequence diverges. Okay, so what is series? An infinite series is an expression that can be written in the form of a1 plus a2 plus da da da. So you're adding all the terms in the sequence. So it's a sum of all the terms in the sequence. And so the number a1, a2 are called the terms of the series. Okay? And you can see here k is the index. So this is the summation notation. So sum k from 1 to infinity of a sub k. Okay. Next, the sequence of a partial sum, s sub n. So the sequence has a partial sum, is itself a sequence. So you can see how it constructs. The first term S1 is the sum of the first term. The second term S sub 2 is the sum of the two terms. And then the nth term of the sequence of partial sum is the sum of the first n terms of the series. Okay. If the sequence of the partial sum S sub n has a limit L, then the infinite series converges to that limit L. So we have the series, okay, that is the sum of all the terms in the sequence equals to the limit and goes to infinity. This is the partial sum, okay? And notation, so that's the limit n goes to infinity of s sub n. Okay, that equals to L. If this guy, this is a sequence of partial sum has a limit, then the series also converges to that limit. If the sequence of partial sum diverges, then the infinite series also diverges. So diverges means the limit does not exist. It's like infinity. Okay. So the remaining sessions of this chapter, we will learn different kinds of series, and we'll talk about when multiple tests to know whether the series converges or diverges. So the first series we study is the geometric series. Okay, so a geometric series, sum a r to the k minus 1. So if we write this out, we have the first term a, and then each term we multiply by a factor of r. So this is the second term, and this is the third term. So each term we multiply by a factor of r. Okay, so we can use this notation if we use the index k when k start with 1. Okay, then you see the first term k start with 1, so it's a, so there's no r in it, so that's why it's r to the k minus 1. But if you let the index k start from 0, then the expression is going to be a times r to the k, because r to the 0 is 1. So when you plug in r is 0, you get the first term is a. Okay? So these two different notations actually represent the same series. Okay? So this geometric series converges if the absolute value of r less than 1. Okay, the ratio r is less than 1. And the series diverges if the absolute value of the ratio r is greater or equal to 1. If the series converges, then the sum is this guy. Okay, so how do we prove that? Alright, so let me show you the proof. Okay, so let's call the nth partial sum as equals to a plus ar plus ar squared plus plus ar to the n minus 1. Okay, and then so this is the nth partial sum. There is the sum of the first n terms of the sequence. Okay, and let's look at if we use r multiplied by the both sides, we get ar. So ar, I want to put it under the ar. And then ar times r is ar squared. And then we have ar to the n minus 1. And the last term, this guy, multiplied by r, will actually give us ar to the n. Sorry, r is downstairs. Okay. So I'm gonna use the first equation, subtract the second equation. Then what do we get? We get 1 minus r times s equals 2. So you can see this cancel, and this cancel. So we will have a minus ar to the n. So we can solve for s. So s is, we can also factor out the a and 1 minus r. So far so good, everybody? Okay, so let's separate into cases. So first case, if r equals to 1, what happened? Well, if r equals to 1, then the series just like a plus a plus a plus all the a, we know it diverges because a is now 0. Okay, it's either infinity if a is positive, or it's minus infinity if a is negative. Okay, and how about if r is minus 1? So if r is minus 1, then our sequence becomes like a minus 1, a plus a minus a plus a. So it's always oscillating between 0 and a. Okay, so this guy also diverges. Okay, because it's oscillating between two numbers 0 and a. Okay, and 3. So if our absolute value of r is not equal to 1, so what happened? Okay, we can see here, if absolute value of r less than 1, then we get the exponential function. Okay, so if r is less than 1, so the exponential function r to the n is actually a decreasing function. So when n goes to infinity, okay, so when n goes to infinity, a times 1 minus r to the n over 1 minus r. So this guy will go to 0. So that's why we have a over 1 minus r. Okay, and if absolute value of 1 over absolute value of r greater than 1, then we have a increasing exponential function. So it will go to infinity. That's why the limit diverges. The limit does not exist. Okay, we say the limit does not exist, then the series diverges. Okay. Alright, so that is the proof. So when we see a geometric series, the first thing we gotta do is to figure out the ratio. And then if the absolute value of the ratio less than 1, we have series converges. And if the absolute value of the ratio greater or equal to 1, we have the series diverges. Okay? And when it converges, what does it converge to? So I hope that you can remember this formula. So instead of A, I hope you can remember is the first term over 1 minus the ratio. Okay, if the first term is not A, so this formula is not necessarily A. It's whenever the first term of the geometric sequence. Okay, so let's look at examples. So example 1, part A. Evaluate the following geometric series or states that series diverges. Okay, so let's look at the first one. What is R? R is whatever under the exponent k. So in this case, R is 1.1, and that's greater than 1. If the absolute value of R is greater or equal to 1, then we get the series diverges. Okay, everybody? The series diverges. Okay, and part B. What is the R? Is the R E? No, actually no. So what is R? So you can rewrite this problem to be e to the minus 1 to the k. So that is 1 over e to the k. So your r is actually 1 over e, which is less than 1. So we have series converges to, okay, to what number? So it's the first term. How do we get the first term? Well, you look at your k start with 0. So you plug k is 0 into the formula. So we get e to the 0. E to the 0 is 1, and then we have 1 minus the ratio. Ratio is 1 over e. So we have, let's simplify it. Let's multiply by e on the numerator and denominator. So we have e over e minus 1. All right. How about the next one? The next one, okay, we have, so R is whatever under the K, okay? So R here is minus 0.75. So absolute value of R is 0.75, which is less than 1. Okay, so series converges. But converge to what? It converges to the first term. The first term is, you plug in k is 2. So it's 3 negative 0.75 squared. 1 minus r. The ratio r is negative 0.75. What is that? That's like 3.75 is like 3/4. So 3/4 squared is 9 over 16. And then 1 minus that is like 1 plus 3/4 is 8 is 7 over 4, right? Okay, what is that? Well, you can see this cancel, we get 4 there, and that's the same as 3 times 9 is 27 over 4 and over 7, so 28. Okay, everybody? Alright, let's continue. Example 2. Evaluate the geometric series or states with reason that it diverges. Okay. So let's see. The first one. Oh, I see the k here. I see the k here. So let's make it into the standard form. The standard form is either k start from 0 or 1, doesn't matter. The standard form is we have a times r to the k. So we want to group all the things under the k together to beat our ratio r. So here, let's see. The first one, negative means we actually can flip it. And next we can split. This is 2 to the cube, right? Times 2 to the negative 2k. Well, let's continue. So 5, 3. Okay, so here 2 cubed is actually 8. So you can actually put the 8 in front. And then what's next? This is like 2 to the negative 2 to the power of k. 2 to the negative 2 is in fact 1 over 2 squared, which is 4. Okay? And let's continue. So we have k from 0 to infinity. 8 stay here. And then we combine all the things inside the k. So 5 in the numerator, 3 and 4 in the denominator. That gives us 12. Okay, so what is k now? Sorry, what is r now? R is whatever inside the k. Okay, so r is 5 over 12, which is less than 1. Then we know the series converges to... We have the first term. First term means you plug in k is 0. Well, when you plug in k is 0, you just get 8. And then 1 minus the ratio 5 over 12. So that is 7 over 12, right? So that is let's see. So 8 over 7 over 12 is the same as 8 over 7 times 12. So we have, is it 96 over 7? Yes? Okay, so that is part A. Let's continue and look at part B. So I hope now you can pause the video and try to work on it by yourself first. Okay, are you ready to continue and check the answer with me? Okay, first of all, we gotta split the constants and the k powers, okay? So we have 2 to the 4k times 2 to the negative 2. Split the exponents. And here we have 7 squared to the k. Split them. Okay, so this is constant. We can move it in front. So 2 to the negative 2 is 1 over 4. And then 2, so 2 to the 4k is like 2 to the 4 to the k. And downstairs we have 7 squared to the k. So we can actually group them together. So what we are doing is make the problem into the standard form. Then we'll be able to see what's the ratio. 2 to the 4 is actually 16. 7 squared is 49. Alright, so I got okay. Alright, so I got my... Okay, so this is my R. You can see R here is still less than 1. So we still have a series converges. Okay, so series converges to what number? The first term. Oh, let me do it. First term, which is when k is 1. See, when k is 1. So when k is 1, when k is 1, we have 1/4. K is 1/16 over 49. 1 minus r. R is 16 over 49. All right. And so what is that? Well, this cancel. We have 4, so 4 over 49. Here it's like 49 minus 16. Is it 33? Yes. So 33 and then 49 cancel. We have 4 over 33. So far, so good, everybody? So that is our answer. Let's go to the next problem. Okay, so the previous problem we are given the formula, but this one we're not given the formula, but it's okay. We can figure out the formula by ourselves. How? Let's compare them. Well, what's the difference? Well, I see the term plus minus, so alternate. Alternate means it should contains a factor of -1 to the n or a factor of -1 to the n plus 1, depending on what's the index. Maybe it's better to use k. I use k a lot for the index in the series. Okay? And you can see we have numerators and denominators. So the first one, let's A1. So A1 is positive. Okay? So A1 is positive, it's positive 5. A2 is negative. And negative, what's the 10? Well, 10 is like 5 times 2, right? And the bottom is like 3. A3 is positive, but 20. What is 20? 20 is like 4 times 5, right? And the bottom, we have 9. 9 is 3 square, right? And the next one, A4. A4 is what? A4 is negative, so negative 40. 40 is like 5 times 8. And then this is 3 cubed. So actually, you can see the ratio of the previous term. Here, the ratio is 10 over 5 is 2. So 2 over 3 and negative of that. And then this one, the ratio is also negative 3 over 2. This one, the ratio is negative, 2 over 3. And negative 2 over 3. So that's why we can think of A1. A1 is like 5 times negative 3, 2 over 3 to 0. And A1 is 5 times negative 2 over 3 to the, A2 to the 1. And then A3 is 5 times negative 2 over 3 to the second. So that's why in general, A sub k equals to 5 times negative 2 over 3 to the, if this is 3, then this is 2. If this is k, what is the exponent? K minus 1. Okay, so that's why this guy is the series k from 1 to infinity, 5 minus 2 over 3 to the k minus 1. Okay, so that is why we can also express if I let my index. So if I let my index k start with 0, then well this guy is, if my k start with 0, then this guy is like A0 or A0. It match with the 0, right? So, and then this is like A1, it match with the 1. So in this case, we have 5, negative 2 over 3 to the, k. Okay, so it really depends on how your index, whether your index start with A1 or your index start with 0, then the first term is A0. Okay, so here you can see my R is whatever inside my, oops. What did I do? Come back. Yes. Okay, come back. All right. Okay, so here, this is my R. You can see absolute value of R is 2/3, which is less than 1. So this series converges. It converges to the first term. So first term is when you plug in k is 0, right? So that's why you have 5 is the first term. 1 minus the ratio is negative 2 over 3. So that is 5 over 3. They cancel. So the answer is 3. Okay, everybody? So the answer is 3 for that problem. All right, so let's continue. So we have learned geometric series. You first need to figure out the standard form, which is a times r to the k. And so you group all the things inside the k together. So that is going to be our ratio. And then look at the ratio, whether it's positive, whether the absolute value of the ratio is greater or equal to 1. Then we have series diverges. If we have the ratio, absolute value of the ratio less than 1, then the series converge to one number, the first term over 1 minus the ratio. Alright, so the next series is the telescoping series. So what is the telescoping series? Well, there's a special properties about the telescoping series. So the telescoping series, okay, so the telescoping series is you can express your AK in terms of something subtract something. Okay, and this is the first step. And second step, you compute Sn. So Sn is at A1, A2, A sub n. Okay, and then you're gonna put down what it is, and then you will realize a lot of terms get canceled. Okay, and then you get a formula about n. And the third step is the series. The series is the limit of Sn where you let n goes to infinity. Okay, so let's look at our problem. So our problem, first of all, we want to express this as a difference of two things. Well, this is a sub k. A sub k, using the properties of logarithm function, is natural log of k plus 1 minus natural log of k. This is the first step. Well, the second step is we compute Sn. Well, Sn is A1 plus A2 plus A sub n. Well, what's A1? A1 is we plug in k equals to 1. We plug in k equals to 1, so we get the ln of 2. Minus, we plug in k is 1, so we get ln of 1. So this guy is actually just A1. Okay, this is A1. And then A2 is when you plug in k is 2, we get ln of 3 minus ln of 2. So that is A2. Plus ... What is the last term? Well, the last term is A sub k. So you plug in A sub n. So you plug in k equals to n. I want to write more. I want to write one more term in front of it. I want to write A sub n minus 1 term. So that means you plug in k equals to n minus 1. So we have ln of k minus ln of n minus 1. Okay, so this is A sub n minus 1. And then we have A sub n is plug in k equals to n. Okay, and then we do a lot of cancellation. What can we cancel? So you can see here, ln of 2 cancel. So actually ln of 3 would cancel with something inside the ... And here, how about the last two terms? You see ln of n cancel. So actually this guy will cancel with some terms in the ... Okay, so what is left? Well, what's left is minus ln of 1 and plus ln of n plus 1. Okay, so I want to say it one more time here. Okay, so the trick is only half of the term of A1 survive. So only half of the term of A1 survive. Only half of the term of A sub n survive. And which, usually the first one, A1, is easy because you just look at which one cancel with A2, then you know which term survive in the A1. But how about A sub n? And I can tell you the bigger index will survive. Okay. All right. So that's why here the index, this is index n, this is index n plus 1. So n plus 1 is the bigger index. So the bigger index term will survive. Okay. All right. So this is step 2. Step 3. So step 3. S infinity is the, oh, by the way, ln of 1 is just 0. So this is ln of n plus 1. And when n goes to infinity, ln of n plus 1, well, remember, natural log looks like this. Oh, sorry. It will go up all the time. So that's why this is infinity. So we have the series diverges. Okay. All right. So that is the telescoping series. Okay, so we have one more here. Remember, once the first steps, we want to decompose into a difference of two terms. So how do we do this? Well, you can actually multiply by the conjugates. Okay, what's the conjugate of that? I would say the square root of k minus square root of k plus 1, square root of k minus square root of k plus 1, right? So you multiply by the conjugate, and then what's the top? The top is gonna be square root of k minus square root of k plus 1. The bottom, let me use a different color. If we are doing a German formula, we have a plus b. A minus b is a squared minus b squared. So that's why we multiply by its conjugate. Okay. So then we will get the bottom. The bottom is k square root of k squared, so it's k minus square root of k plus 1 squared, so we have k plus 1. So this k cancel, we have minus 1. What will minus 1 do? It will actually flip the term on top. Okay, so the terms, they reverse order. So we have the negative 1. That's the effect of the negative 1. Okay, so now we can see a sub k is the difference of two terms. So the first step, a sub k is the difference of two terms. Second step, S sub n is then a sub 1, a sub 2, a sub n minus 1, a sub n. So if you get used to it, then you don't need the a sub n minus 1 term. But because now we are still new to this kind of problems, so it's good to write it down. Okay, we plug in the first term when k equals to 1. So we have square root of 2 minus square root of 1. That's a1. A2, we plug in k is 2. So square root of 3 minus square root of 2. That is a2. A sub n minus 1, we have square root of n minus 1 plus 1 is n. And then we have n minus 1. So that is a sub n minus 1. And the last term, we plug in k equals to n. So we have n plus 1 minus square root of n. So this is a sub n. Okay, now let's cancel. So let me use different colors. So here you can see square root of 2 cancel. And square root of 3 will cancel with something inside the dot dot dot. Here, see, square root of n cancel, and this guy will cancel with something in the dot dot dot. So what is left? Well, we have square root of 1 is 1, and then the bottom, the end, we have square root of n plus 1. Okay, so see, the bigger index. Okay, so the bigger index term will survive. Okay, so, or will stay here. So that is the second step. And then the last step, as infinity is the limits n goes infinity of this guy. Oops, when n goes to infinity, what is that? Well, it goes to infinity, so we still have series diverges. Okay, everybody? All right, example 5. Okay, so part A, we want to evaluate that. Well, first of all, let's call this is A sub k. We want to express A sub k as the difference of two terms. Well, here, what can we do? Partial fraction. You see the denominator k and k plus 1, partial fraction. So you can set it up as like a over k plus b over k plus 1, and then you clear the denominator, so this guy equals that. When you clear the denominator, you get 1 equals to a times k plus 1 plus b times k. You plug in k is 0, you get 1 is a, b is 0. Oh, so a is 1. You plug in k equals to minus 1, you get 1 equals to the a term is 0 and then minus b, so b is minus 1. Oh, so ak is a is 1 minus 1 over k plus 1. See, actually, even though we are in chapter 8, we actually need some concepts in chapter 7, the partial fraction. Okay, that is the first step. And second step, we want to find the Sn, the first n partial sum. Okay, so that's a1, a2, dot dot dot, a sub n. Okay, if you get used to it, you don't need to do a sub n minus 1. Okay, so a1 is when k is 1. So 1 minus, when k is 1, we get 2. So this is a1. a2, when k is 2, 1 over 2 plus, minus 1 over 3. Okay, and then plus dot dot dot. When we plug in n, we get 1 over n minus 1 over n plus 1. All right, so let's start to cancel. Oops, this is a2. This is a sub n. Let's start to cancel. You see that 1/2 cancel. 1/3 cancel with 1/3 somewhere in the dot dot dots. Here, which index will survive? The bigger index survives, so 1 over n will cancel something inside. Okay, what is left? What's left? We have 1 minus 1 over n plus 1. Great, because the third step, when we let n goes to infinity, we'll get 1 minus 1 over n plus 1. So the 1 over n plus 1 will actually go to 0. So this guy goes to 1. Wow! Series converges, and it converges to 1. Okay? Let's see here. That is part A. So we actually find that the series converges to 1. Part B. Use part A to show that 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus plus 1 over n squared less than 1. Okay. All right. Okay. So what is that? Well, so start from part A. So from part A, what do we learn from part A? When you plug in case 1, we get so from part A, when we plug in case 1, we get 1 over 2 plus 1 over, when k is 2, we'll get 2 times 3 plus 1 over 3 times 4 plus 1 over 4 times 5 plus equals to 1. So this is part A. So we kind of we want to have 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus plus 1 over n squared. We kind of want to show that we have something here. And that guy is also less than 1. Okay? You can see this limit is 1, but if we have this is a limit, but actually is less than 1. It's just approaching to 1 when n goes to infinity. Okay? Yes, that is because this guy is less than 1, but it's just approaching to 1 when n goes to infinity. Okay, so what do we want to put here? This is like a bridge, right? You have one island, you have another island, you want to build a bridge between them. Okay, let's compare. So now let's see this guy. So 1 over 2 squared, we want to show it's less than some number. Okay, some number of some of this form. But let's see. Let's look at the denominator. The denominator is 2 squared, right? Well, 2 squared is greater than 2. So this guy is less than 1 over 2, right? So this guy is less than 1 over 2. How about the next term? The next term is 1 over 3 squared. We want to compare with 2, 3. Well, 3 squared and 2 times 3, of course, the 3 squared is bigger. But when you flip it, then we get less than. So this guy is less than. Well, so in fact, if we continue this process, you will see that 4 squared is greater than 3 times 4. So this guy is, oops, we flip the inequality sign. So we have less than. So now what's the pattern? This guy will be less than what? See, if it's 4, then the later index is 4. So if it's n, then the later index is n. Then the previous one is n minus 1. So what do we fill in here? We filled in 1/2, 1 over 2 times 3, 1 over 3 times 4, 1 over n minus 1 times n. And this guy less than 1, because when we add infinite many things, it's still less than 1. So when we add smaller things, then the answer is also less than 1. Okay, so that finished the proof of part B. So part B is like a math contest problem. So part A is more like a computation problem, given a series and asks you to find to show whether it converges or not. Okay, so part B is a little bit challenging. Okay, so that is session 8.3. When you have questions, feel free to print screen and ask me. Bye.